an estimate of the percentage of noise that's contributed by shearing versus just plain engine thrust and mechanical noise?
I don't have a number.
Is it a larger portion or a smaller portion of noise?
It's a very large portion.
Majority or?
It's the majority. So there's jet noise and there's turbo machinery noise.
Right.
The jet noise is very dominant, and that's one of the reasons why you tend to have very high bypass ratios. Yeah, you definitely can hear it when you compare the fighter engines to the big commercial engines. Here's an example of improving the jet noise by a special geometry of the nozzle, the bypass nozzle. And that's a thing we'll maybe see on the 787 already, flying, and I think also the 747-8 come up. The point is that applying active control, you can even optimize the geometry. In this case, there were shape memory alloys involved in this little parts of the nozzle. That's this part here. This nozzle gives you a larger mixing between the jet and the outside flow. It just involves a very high level of turbulence. And this turbulence then increases the mixing. And the problem is that by introducing such a turbulence level, you have losses as well. Aerodynamic losses, which decrease propulsive efficiency. So the challenge here is to optimize the geometry for noise, of course, and also for efficiency. And so that's the point of active control. You can optimize for specific mission points. You optimize for noise during takeoff and landing, and then you optimize for efficiency and thrust during cruise. So you've got those two settings, and therefore shape memory noise are quite fitting in terms of a technology, because shape memory alloys have got two geometries which can be changed to levels of material.
Question. What is actually being actuated by the SMA? What physical geometry, geometric feature?
It's this part here, this triangle.
Okay.
These are the SMAs.
You're basically taking the flap in and out. The flap, exactly. the nozzle, the serrated end. So basically reducing the area, opening the area.
Oh, so those little triangular
triangle goes into the flap, moves in and out.
Okay.
In and out of the jet, and into the jet.
So like, kind of varying the nozzle area a little bit.
Okay.
So displacement is not big, but has a large effect. There's another technique of the nozzle, which is called thrust vectoring. It's not a new technique, it already exists on the F-22 and also has been demonstrated for the Eurofighter. Today, it's an actuation which is done mechanically, and you change by moving the nozzle mechanically, you change the direction of the jet. And therefore, you can change the force vector, which the aircraft will see. You can see here in the two-dimensional or three-dimensional region. So given side angles and upwards and downwards angles. The thing is that you even can replace conventional control surfaces in the aircraft just by moving the direction of the jet. And this is especially interesting for UAVs, unmanned air vehicles, where you maybe have very demanding maneuvers. So you don't have the restriction of the human being inside and seeing G-forces, but you can think of any maneuver possible. And therefore you could replace the control surfaces by moving the direction of the high-speed jet. This can also be done by fluidic actuation, which is done today already in helicopters, applying a Grinder effect. Problem is that fluidic actuation in the nozzle means also that you've got to take high bleed air. So again, that's the trade between the gain and the investment. Okay. So I would like to end with some concluding remarks now. We saw that active control offers some promising performance benefits for fuel burn, for emissions, for operating range, and for weight and cost. And that's basically the thing an engine designer is looking for. We saw that promising concepts have been demonstrated, but they all have been on a laboratory level still. It's also an important point. The challenge is now that we've got to drive these technologies from the laboratory towards the real application. And there's still a lot of challenges to solve, and some points which need to be addressed. There's the point of size, weight, and cost of the actuation elements. Cost maybe the sensors, which are very costly. And also life, which is not addressed here, but it's a very important thing for the sensors. All these systems have to be installed in the engine in a very harsh environment, not easy to pass. And then once you have got that in the application, the whole thing has to be certified. And that's a point where we don't have a solution yet, but which needs to be addressed. And the big point is the failure handling. Because when you design the engine with active control, you completely rely on these systems. And once they fail, you need a backup solution. So that's a challenge I would like to give you now. So I hope that we'll see some advances in the future here. Yeah, that's all from my point. Do you have any questions?
Failure handling could be probably addressed as for an example, in vehicle suspension. You have a spring and a damper, and the damper is busted. The car still functions. You don't have comfort. The car will behave probably a little bit hectic, but still runs and it's safe, right? So probably that would be a fail-safe approach.
You need to find solutions where failures don't lead to a catastrophic event. One thing, for example, of clearance control.
Yeah, that is essential, absolutely.
Yeah, you have to design a device which opens the defects. You mustn't close.
Right. You lose performance, but you
lose performance, you lose operability. You somehow have to treat for that.
Right.
Well, in sensing and application of MEMS devices, one design route could be to add a lot of redundancy that's possible if it's low cost. If you have low cost sensing elements or MEMS-based devices, then you can say, okay, I put in 10 or 15 such elements, and if 4 or 5 of them fail, I still have sufficient functionality. But that's something that would be a radically new architecture, and currently, as already mentioned, we don't have this benefit of large numbers of sensors or whatever that can be reduce the price as in automotive applications where a sensor just costs a few, 1 or 2 euros something. Yeah, and in aerospace we not yet have only reached the bottom of this curve that gives us a cost reduction there. But one could think of designing redundant systems.
Could you think of designing a machine that could not reach part of its mission without active control, and therefore could not get back without it? Because they talk of aircraft that can only fly, are inherently unstable to fly. Therefore, why couldn't you have a gas turbine that is inherently unstable?
Why couldn't you?
Why couldn't you? If you can have an aircraft, why couldn't you have a gas turbine that's as brave as that?
Well, currently we have got the requirement that this case is not certificate. So
If you have a human pilot in it or human passengers, the story might be seen different if it goes for UAVs or UCAVs. There you might trade capability against enhanced risk of loss.
Yes.
That could be possible. If it's low cost, high volume, why not?
See, in aircraft, there is a requirement for maneuverability. Maneuverability for fighter aircraft, maneuverability is inversely proportional to stability. So there is a drive to have instability. So there is a performance requirement. So unless there is such a performance requirement that you want to operate in certain zones where you have to, operate instability, there is no such requirement. So right now, your trade-offs are all done on a passive basis.
Yeah.
So you build in a lot of conservativeness in the operation to make sure you will stay safe
Yes.
in all kinds of extreme conditions. So the idea is here of active control technology is more of making sure that in general you can operate at higher efficiency, and then active control technologies kick in only when you need it. That's the idea.
Yeah, in land-based gas turbines, you don't have this overriding need to be operating at all sorts of
operating
regimes.
conditions.
There's pretty much like 2 regimes,
Yes.
transient and steady state.
I mean, like, for instance, if you look at it, there's a stall margin requirement for compressors. The stall margin requirement comes from being able to take off in crosswind. Okay, so that's the worst case situation for distortion that the inlet sees for commercial aircraft.